In the previous section, we introduced a so-called causal mask to hide future words in the input so that the LLM can't cheat and access future words when it's generating the next word. Now we are going to introduce another type of mask, a so-called dropout mask. So what is the dropout mask? So the dropout mask will pick random positions in this attention weight matrix and then mask them out. And so dropout is a very popular concept in deep learning and has been around maybe for 10 years or longer. And it's just applied to various layers to reduce overfitting. And similar here, we can apply a dropout mask to the attention mechanism so that the model learns to rely less on certain positions. So here it's just a random selection of certain positions. And then we apply this mask on top of our causal mask to mask out these positions. And you can see if we apply this mask to things that are already masked out here above the diagonal, nothing will happen. But it will additionally also mask out certain things in the input to reduce the reliance on these positions to reduce overfitting. I should say, though, this is not very commonly used anymore when training LLMs. I'm adding it here for completeness because the OpenAI team for the GPT-2 model, they used a dropout mechanism, but more modern LLMs, they are not using it anymore. The reason why I'm introducing it here is just for completeness so that we are implementing the original architecture. But if you are training LLMs, you can also just deactivate that or just omit this dropout mask. But just for completeness, let's see how dropout works, how we mask these things. So luckily, so PyTorch has a layer called Dropout. So it's actually quite simple to add this on top of our existing procedures. And it asks you to specify the dropout rate. So 0.5 here means 50%. So this means, for example, we are dropping half or 50% of the positions. So let's assign this to layer. And then let me also add a random seed, torch manual seed, so that you hopefully get the same results that I do. However, I should say there's one thing that is particular about Dropout, and that is that it has a little implementation detail or bug, depends on how you want to call it, in PyTorch, that on certain hardware or operating systems, it is not fully deterministic. So you might get slightly different results. I reported this a while back to the PyTorch team on the GitHub tracker, so it's not resolved yet because they said it's not a high priority issue, because I guess Dropout is not that popular in the first place anymore. But so just that you are aware, you might get slightly different results, but that doesn't really matter that much. Now, one more thing, just to toy around with a simple example, let me create a tensor of ones. Let's do a 6x6. So it's exactly the same size as our attention weight matrix. And so I can now call layer example. So I'm calling my dropout layer on this example, and let's see what happens. So what you can see is certain positions are zeroed out now. So just random positions here. By the way, if I change the random seed, you will see it's different positions. So it's just a random way of masking out values. Now, one thing here is though that the other values, notice that they are now larger. And so why is that? So to maintain approximately the same sum in each row, it is rescaling the values. So for example, the formula is, I think it should be 1/1 minus dropout rate. So if we have this formula here and my dropout rate is, what did I say, above 0.5, if I put 0.5 here, this should come out at 2. So if I have a smaller dropout rate, this should be then a different value. So we are essentially rescaling our values here to account for the fact that we are missing certain values. So it's just so that if you consider fully connected layers, the next layer that receives the output from this layer, it receives about the same summed value. So if we would sum those values and these, they should be in the same order of magnitude before and after. Of course, this is a very small example, so it doesn't, let's say, turn out as nicely that it is exactly like that, but it's the rough idea that when we reduce half of the values here, if we remove half of them, the other ones are scaled up. So it's compensating for that. And yeah, and so this is essentially how Dropout works. And then we can apply our layer to our attention weights, and then have the dropped out attention weights essentially. So this mask is what you are seeing here. And now we are again one step closer to completing the engine, the attention mechanism for the LLM.
Get this book at manning.com.